Good evening, everyone. This is Manjeet, the TA for this course, Nature and the Properties of the Material. Today we will discuss the assignment number 8, and this will be the last assignment for this course. And if you have any doubt, you can put your doubts in the chat box, or you can raise your hand and can ask also and verify that one also. Okay, so today in this lecture, because this 8 assignment 8 is basically based on the XRD and the defects in the materials. So we will do the some problems based on that XRD and the defects. We will continue one by one, and we will get an idea how we approach these XRD problem and the defect one. So okay, so hmm, let's start this assignment number 8. Okay, in just a second, there is some oh, these are no synced yet, so just wait. Oh, it's not. Okay, let's continue with one by one, and meanwhile maybe it will get fixed. And okay, so in question number 1, which of the question number 1 asks the which of the following is and are correct about the X-ray diffraction from the crystal. So you know the XRD, how the this diffraction happen when the XRD are incident on the crystal and they form the interference pattern there, and then you will get the peak diffraction for the certain peaks and the for certain HKL value, and there will be their destructive diffraction also there is no peak there. You will get the zero intensity, or somewhere the minimum intensity is there also. So this is all about XRD. So you have to tell, so which of the following are the correct statement. In A part, it is asked the structure factor is dependent on of the shape and size of the unit cell. In B part, it is the intensity of the peak is proportional to the square of the square of the structure factor. And the C part, the structure factor depend upon the position of the atom in the unit cell. In D part, structure factor is dependent on the atomic number of the elements in the crystal. Okay, you know the phase difference that is happening between the two cell is of phi is equals to 2 pi h u plus kv plus lw, and the corresponding the scattering wave that is with having this phase difference between them is if the form of a e raised to power iota phi, and this will give you a exponential of iota 2 pi iota h nu plus kv plus lw. And the this for if this is for the one atom, and if I talk about the for the n atom, for n atom it will be the, if I say this corresponding structure factor corresponding to HKL will be the summation of I is equals to 1 to n. Okay, and this is f, let's say this is n, not because I is represent here iota also, so I'm taking this n. So small n, let's say this is small n, so this will give you Fn, and exponential of 2 pi I, of which atom I am talking about, H Un plus K, Kn plus L Wn. I have to consider all the atoms that are present in that unit cell and the corresponding position, because U, V and W are the position of the atom of the unit cell. Okay, so this is for the n atom. If I have the n atoms in a unit cell, for the structure factor will be this in the, and this F is basically we call this the structure factor. This is equals to amplitude of the waves, amplitude of wave scattered by all the atom in the unit cell, divided by the amplitude of the wave scattered by the electron. And you know this intensity is directly proportional to this F structure atom. Also there is also an atomic structure factor, and this geometric structure factor. Because of the atomic presence there will be some structure factor, and also the this geometric, and where we consider the UVW, these are the geometric, and otherwise they there is also a atomic structure factor that's on which your intensity depend. Okay, so in this question it is the structure factor is depend upon the shape and size of the unit cell. Nowhere it is mentioned that it is depend upon the shape and the size of the unit cell, so this is not the correct answer. Let's move to the next part. The intensity of a peak is proportional to square of the structure factor. Yes, this intensity, because my intensity directly proportional to the square of the structure factor, so B is your correct answer. And the now in the C part, the structure factor depend upon the position of the atom in the unit. So you can see here this your F factor, this is depending upon your U, V and W. These are the position of the atom of the unit cell. If this will consider all the atoms that are present in the unit cell, it's if in the simple cubic, it will be the number of atom will be the one. So there will be one UVW. In the BCC we have the two atom in the unit cell, so there will be the two UVW set, and the in FCC we have the four atoms, so we will have the 4 UVW. So we this depend upon the where my atom is present in the unit cell, the position of your atom in the unit cell. So UVW this will define, UVW basically define. Oh, okay. Okay, this UVW, so this structure factor also depend upon the position of the atom in the unit cell. Okay, so then C is also the right answer. In the D part, the structure factor is dependent upon the atomic number of the element in the unit cell. Yes, that also depend upon the structure on the atomic number, because it define the number of the atom that are present, how many are the electron, because this F also depend upon the this depend upon the electron, your wave scattered from by the an electron. So this also depend all the atoms, how many electron are that are present in your atom. So structure factor is also depend upon the atomic number of the element that in the crystal structure. Okay, okay, this is all about the question number one. Let's move to the question number second. So in question number second, it is asked the first three peak in the XRD pattern of a FCC structure material. You know FCC1, so there are the parameter where which of the uh, I mean the which of the diffraction of which are the HKL value are your which one are the HKL value are the allowed one for the FCC simple cubic. You know in the simple cubic all HKL are allowed. And if I in the BCC, if I talk about in BCC, if HKL plus 1 HK plus L is even, then it will be the present in the there will be the diffraction peak corresponding to that HKL value. And if it is the HK plus L equals to odd, so there will be the no diffraction peak exists in the pattern. Okay, if I talk about the FCC one, in FCC, if all HKL are either odd or even, then we will get the diffraction peak. Otherwise, there will be no diffraction peak. Okay, that means if your individual all HKL value are either odd or either even, and if they have the mixed behavior, so mixed behavior, then there will be the absence of your diffraction peak. You will not get a peak corresponding to the that HKL value. Okay, so this is the criteria. So if you see this in this question, it is asked about the FCC. So for the FCC, if all HKL are either odd or the even, then we will get the peak corresponding to in the XRD pattern. So if I go to the A part, in A part, 100, 111, 200. So here it is the mixed behavior 100. One is odd and 00 are the even integers. So this is not for the FCC. This is not allowed in the FCC pattern. If I go to the B part, so this is 111, 1 to 1. Here there is again this is the mixed behavior. So there is absence corresponding to this part. So this part is also the incorrect part. In C part, 200, 311. These are all even. These are the all odd and these are the also even. So this is the correct. These are the these are the allowed HKL value for the FCC structure material. And if I go to this one also, this is 111, 200, and the 220. So this option also satisfy the condition of the FCC structure, or either all are the odd and either all are the even one. So this is also the correct answer. But in the question, it is asking about the first three big. So which one will be the first three peak? You know, though for this FCC one, we have the this okay, this will come first. This will, because this h square plus k l square plus l square will be the, for this one will be the 3. For if I talk about the this corresponding to 111 will be the 3. 200, it will give you the 2 square plus 0 square plus 0 square, that is equals to 4. Corresponding to now is next one is 220. So this will be, if I go to 2 square plus 2 square plus 0, that is giving you 8, and 311 is correspondingly giving you 339 plus 1 and plus 1, that is 11. So only these are the first, so this is the first, these are the first three peak in the XRD pattern that is giving the FCC structure one. Now from these one, these are the first because this come in later, so this will come later. So these are 111, 200, and 220 are the first three peak in the XRD pattern. So this is the correct answer, and that will give the first three peak in the XRD pattern of a face FCC structure material one. So D is the correct answer. Okay, now let's move to the question number third. There is some This is not synced. I mean, because it is showing the question number one and two are either they are the mixed kind of. So I don't know what's thing that it should be not like that. Oh, that is not showed here, I guess, because there is showing something. Okay, that's not a big deal. Now let's move to the justice. Okay, let me rejoin this one. Just a sec. Now this is right. So in the next question, it is asked in a powder diffraction experiment using the copper radiation of the wavelength of 0.154 nanometer, the first five peaks are observed from a monoatomic cubic structure when the 2 theta is your basically 2 theta is my 38 degree, 44.2 degree, 64.4 degree, and the 77.2 degree and the 81.4 degree. Okay, so what is the crystal structure of this spectrum? So we have to find, we have given the position of the first five peak of the cubic structure, whether it will be the simple cubic, body centered, base centered, or the diamond cubic. We have to find out which of the crystal structure this is having. So how we will proceed this one with this one? If you know that, because it is given the this simple cubic one. I mean the for the cubic structure we know that the, if I somewhere know for the cubic structure we know the structure is that is the where 2d is equals to sine theta is equals to n lambda. Okay, and d is basically your a is equals to under root of k square plus h square plus k square plus my l square. If I put this value, so this is 2a under root of h square plus k square plus l square sine theta is equals to n lambda. If I square this one, because I want to remove this square root, so this will give you 4a square sine square theta divided by h square plus k square plus l square is equals to n. I am considering for the first order, so this will give you the lambda square. If somehow this is, if I can write this as a sine square theta upon h square plus k square plus l square is equals to lambda square by 4 4a square. You know this lambda is constant, because this lambda is constant, it is given this is of the CU radiation of having the wavelength of 0.114, and A is also a constant for the cubic one, so this is constant only, and this theta is varying, and so corresponding to theta we have the different HKL value. So the ratio of this sine square theta and h square plus k square plus l square, if this ratio is constant, the same constant, then we can know about the crystal structure of the this XRD. How we can know? Because we know the which are the allowed plane for the simple cubic. If it is simple cubic, then what are the possible HKL value for the FCC, which are what are the this HKL value, and for the BCC also what are the possible HKL value. We know about this thing, so then simply we can, if we are getting the sine square theta divided by the h square plus k square plus l square is equals to constant value, then we can know, we can find out the this belongs to which crystal structure, either it is cubics, FCC or the BCC. So first what you have to do is, for this one, let's, okay, I'm writing just only the condition here. Okay, so the condition we have is the sine square theta divided by the h square k square plus l square equals to constant value. Okay, how we will calculate the sine square theta, and this will, because as this combination we know for the simple cubic, FCC and the BCC, we will try one by one and then we will continue it. Okay, so for the, if I am taking the, for these are the my two theta value. If somehow I can calculate the theta, so theta will be the this divided by 2, so this is giving you 22.1, 32.2, and this will give you the this 3 8.6, and this is 4 0.7. This is the theta corresponding to these two theta value. Now again, first I have to calculate the sine square theta. What will be the corresponding sine square theta for these one? You have to remember these values. So it will come around the first will come around the 0. You can calculate, because you know the theta value. You have to operate the sine of that theta value and take the square of that value. So it will come out the 0.11. This will give you 0.14, and 0.1, this again multiply by 28, and 0.38 I guess, and 0.42. More or less these sine square theta will come out 0.11, 0.14, 0.28 and 0.38, and the 0.42 for the first five value. Now if I'm considering it is the simple cubic, let's say this is, if this is the simple cubic one, if it is the simple cubic, then we know that the all HKL value are allowed. So what are the first 5p corresponding to first 5 HKL value? So it will be the 100, another will be the 110, it will be the triple 11, then the 200, and the 211. It will be something like this. So the sum will be the h, what will be the h square? Now I'm considering the value of h square plus k square plus l square, because we know because we have to calculate the sine square theta divided by the h square plus k square plus l square value. Okay, so what will be the, for the simple cubic, it will be the 1, first 5 are these value 1, this will give you the 2, 3, 4, 2 square, and this will give the 5. These are the first 5 value, and if you divide sine square theta divided by the h square plus k square plus l square, so this will give you around 0.011 divided by, if you are, this is giving you 0.07, 3 if you divide by the 3, so this will give you 0.9, that is around 9 something, and if I'm going to, this is also 0.09 something. So this is this is not the constant, because this, for the every HKL value, this sine square theta divided by the h square plus k square plus s square, it should be the constant, it not be the variable. So here if you see here, this is changing, I mean this is changing. So these, it means your simple cubic is the these peak that are mentioned here, these are not corresponding to your simple cubic. Now let's move, let's check with the, for the FCC one. Okay, now we will check this the same thing for the FCC one. But now if you know, we for the FCC one, we the HKL call the HKL value are the corresponding HKL value are the, what are the corresponding HKL value? In the FCC one, we have the either all are the odd or either all HKL value are the even. They shouldn't have the mixed behavior. So we will calculate for the HKL if I'm considering the FCC. So what are the possible h square plus k square L value will be the, this will give you the first five will be the FCC one. It means either odd, all odd are given when this is 111, another even or 200, then next one will be the 220, next one will be the 311, and next will be the 222. These are the first five peak in the FCC one. So what will be the h square plus k square plus L square? This will give you the 3, 4, and this is 2 square plus 2 square will be the 8, 3 square 9 plus 1 and 1, that is giving you 11, and 2 square plus 2 square plus 2 square 8, and plus 4 is equals to 12. So the h square plus k square plus L square for the FCC will be the first, for the first for 5 peak will be the 3, 4, 8, 11, and the 12. So what will be the sine square? Because we know the sine square theta value and also the h square plus k square plus L square. We will divide this one and we will get this. If this is the my okay, let me calculate it. How much this is are you getting for, so 0.111 divided by 3 will give you around 0.0366, and 0. If I am say 0.14 divided by 4, this will give you around 0.035 something. And if I'm taking about this value 0.28, or let's calculate this, I mean around this around 8. So this is also 0.035, and 11 also. So this will first 11 3 is 33, so 0.03, and again 5, so this will around say 4, and 12, 12 3 is 36, 12 4 is 40, so this is also around the 0.3. So all are value approximately to 0.03. So this is a constant value. So these the first five peak that are at the angle 2 theta, that is the 38, 44.2, 64.4, 77.2, and the 81.4. 81.4. These are belongs to, these are satisfying this condition, sine square theta plus this sine square theta divided by the h square plus k square plus L square. So this is satisfying, and it is giving you the constant value. So these are the first five peak of corresponding to the FCC one. Okay, similarly if it is not satisfying the FCC one, then you have to check with the for the BCC one. So for the BCC, you know that this sum has to be even. If h plus k plus L is even, so it will give you the peak, and if h plus k plus L is equals to odd, so this is not giving you no diffraction peak. So you have to consider the corresponding h square plus k square plus L square for the BCC if it is not satisfied by the BCC. So you have to check this process for the one by one. For the start with the simple cubic, and the once you calculate this value, you will know what will be the possible h square plus k square value for the simple cubic. I mean on the body center and the fifth center, you can directly write it, and you have to only just divide it and find out to which correct crystal structure it is belonging to. So these peak are corresponding to the FCC lattice. So your C is the right answer for this one. Okay, this is about this question. Let's move to the next question. Okay, so which of the following the diffraction condition for the diffraction from a BCC lattice? So I have already told you, for simple cubic, all HKL value are allowed. For the BCC, if H plus K plus L is even, then allowed. If H plus K plus L is odd, so it is not allowed. In the FCC, either your HKL are all odd or even, then it is allowed. If it is having the mixed behavior, then it is not allowed. So for this of BCC, we have this condition that certify the Bragg's law. So this will give you the first one, the Bragg condition. There will be the diffraction. So the your C part will give you the same criteria that we need for the BCC diffraction one. So H plus K plus L must be even one. So I think so. Everybody know how to calculate for the why this is having, because my structures factor is what is, we have the F, that is exponential of 2 pi iota HU plus KV plus LW1. For the simple cubic, we have the one atom, only one atom. So n is 1 and the position of UVW will be the 0 0. If I put this value, F will be the exponential of 2 pi iota 0 0. This will give you 0 and exponential of 0 is giving you 1. So this is F. So intensity will be the F square. So there will be the intensity of the order of the F square one. For the, this is for the simple cubic. If I talk about this BCC one, for the BCC we have the two atoms. One we are one is having at the center, that is having the coordinate 1 by 2 1 by 2, and another as the origin one, because, and if you calculate this one, so this will give you F exponential of 2 pi I H multiply 0 plus K multiply 0 plus L multiply 0 plus exponential of 2 pi I, this is H divided by half plus K divided by half plus L divided by half, because your UVW are the half value. So this will give you F exponential of 2 pi iota into 0 plus exponential of pi iota of H plus KL plus value. Okay, so this is giving you exponential of 0 is giving you 1. So this is F is equal to 1 plus exponential of pi iota H plus K plus L. So if you know that, if this is my this pi iota value, if your H plus KL plus will be the even value, so this pi this will give you even, that is the 2 e raised to power 2 iota pi. If this is 1, so this is will give you value, it is not equals to 0, so this will give you the 2f and intensity will be the 4f square. If this H plus K plus L value is odd, so this will become the odd value, so this will be the integer of this one value, and this will give the minus 1 e raised to power minus iota, that will give me the 1, and the corresponding will intensity will be the 0. This will become the 0. 1 minus 1 give you 0, so this is giving you. For the similarly for the FCC we have the 4 atoms, so we will the UVW are the possible UVW are the 1 0, this is 0 0, 1 by 2 1 by 2 0, 1 by 2 0, 1 by 2, and 0, 1 by 2, 1 by 2. Okay, these are the four possible. Once you substitute it similarly like this, and you will find the all, if either your HKL, HKL all are odd or even, otherwise it will not allowed. Okay, so this is the way from where you can calculate which of the HKL value are allowed in the which of the crystal lattice one. So the for the BCC, here it is asked about the BCC. For the BCC, HKL should be H plus K plus L, so must be even. If it is odd, then it is not giving you any intensity. So C is the correct answer. Okay, let's move to the next question. So in question number 3 it is mentioned, so I don't know which one is this. Okay, so in the next one, so the crystal structure and the extension condition of the ordered form of the copper zinc 50%, there is, this is the alloy, and this is of the form of the order one, 50% copper and the 50% zinc. So the structure factor and the extension condition, you know this extension condition, what are the extension condition? The condition that that is giving you the allowed HKL value, the or the diffraction condition that is satisfying the diffraction condition, we call them the extension condition. These are the kind of thing are the extension condition. They are not this one, this all are even or the mixed one, these are the extension conditional. So for the this alloy, for this is of the order form of this form, then what will the extension condition? Alloy, we have the copper and the zinc alloy. So in this copper and the zinc, 50% is the copper and the 50% is the zinc one. So which one of the following is the correct condition for this one? So we have in the ordered form, this satisfied the ordered form of the copper zinc, it's satisfied with the cubical behavior. So the whatever the diffraction condition coming from this one and this one, it should satisfy the whole condition, should satisfy, I mean they are having the when they have the zero phase difference, so that it will be the constructive one. If they are having the pi phase difference between them, then they will give the diffraction one. So the in the first part it is in the A part they have, if the this structure factor for the copper and the sum, because how we calculate the alloy one, first thing is the how we will calculate the, for this you have to multiply, I mean the net structure factor, if I say the net structure factor will be the net structure factor will be the F copper plus F zinc divided by 2, this is the net one. And we know that this cubic form, this ordered form of this alloy having the cubic one, so that the all HKL value are the allowed one. Okay, so individually, so this is the net one, so they have mentioned this if FCU plus FZN, so this will be twice of this HKL value. So it HKL should be such that HKL is the such that, so that if this is, I mean, allowed, if this is giving you the some constant value, then it is allowed. If it is not, HKLR says that, so if it is not, so this will not give you the diffraction condition. For this one, this will, I mean, if HKL is the even, H plus K plus L even, so even, this is will be the even, okay, this will give you the diffraction. If FCU minus FGen, because both allow are having the cubic one, so this will there will be the pi phase difference between them, and this will give you the intensity 0. For this, if HKL is K plus L will be the odd, so this is giving the diffraction. So whatever the phase, so there will be the subtract one for the structure factor this way, because your intensity for the sum of in the, if you see in the XRD, there is it's not about the maxima or the minima, either it should be the 4f can know the intensity also dependent. It can be have this intensity or it can be have this intensity, so intensity vary but it's not zero. So the when the this h plus k plus l is odd value, then there will be there is the phase difference between them, and because of this pi phase difference between them, the this intensity will be the f copper minus the f G1. So A is the correct answer. Okay. Okay. Other thing will not satisfy this one. I mean, because it should be the even or the odd thing. If it is odd, so it will not it will be the -1, and if it is the even, then it will be the +1. Okay, let's move to the next question. Now in the next question, the structure of the single crystal are examined by the which of the following method. One, in the last class we have discussion all about the this three kind of the XRD method, that is the powder diffraction method, Lee method, and the rotating crystal method. And the Becerra method is just to calculate the crystallite size or all thing. So structure of the single crystal. Now you have to calculate the for the single crystal. So which of the following in method are the use? You know the powder method is not for the single crystal. Lee method and the rotating crystal method are for the single crystal. And I have, you can see from here, if this is the Lee method, then your wavelength will be the variable one, where your wavelength is varying for this is for the range of the wavelength, and here the incident angle is the fixed one, and the single crystal are examined by this method. And in the rotating crystal one, your wavelength is a fixed but your crystal is rotating, so the angle is variable in this one, and the single crystal are also examined by this method. In the powder one, wavelength is the fixed but angle is varying, but it is for the powder one. So okay, these are the three method of the XRD. So this for the Lee and the rotating crystal method, the single crystal is used to examine the crystal, I mean the crystallography also, or the single crystal are examined by the this Lee and the rotating crystal method. Okay, so B and C are the correct answer. Let's move to the next question. Question number 5. In question number 5, it is asked, in the powder XRD method, the intensity of the various bright lines are compared to the determine the crystal structure. Okay, in the powder XRD, it is the intensity of the various bright light are the compared to the determine the crystal structure. For the simple cubic structure, the theoretical ratio of the intensity of the first two peak. For the simple cubic, you have to calculate for the simple cubic what will be the theoretical value of the intensity of the first two peak. For the simple cubic, if it is a simple cubic, you know that the HKL should be the all HKL value are the allowed one, but theoretical what will be the intensity ratio of this one. So if you know this intensity, so we already told you this intensity depend upon the structure, I mean the structural factor, geometrical and the geometrical structure factor, and the atomic structure factor, or I can say this is the f square s square. This is the geometrical, this is the geometrical structure factor, and this is the geometrical structure factor. F generally we wrote in this, and this is your atomic structure factor. So total intensity depend upon the both the factor. For the simple cubic, the first two peaks are will be the all HKL will be the loss. So the first two peak will be the 100 and 110. These are the first two peaks one. For the this, if I am calculated this, you know what will be the, this will be the A or the F, or I can say this is the capital F, this will be the F exponential of 2 pi iota HV plus K HUKV plus LW, and because UVW for simple cubic it will be the 0 0, so this is giving you F. For the both the intensity, because it doesn't matter where your this H, K and L, because your UVW are the 0 0, so this is the same thing. Okay, this is a, but you know that the multiplicity of, what is the multiply, because multiplicity also of this one that go reflect in your atomic structure factor. So multiplicity of the one this 100 is around 6, and the multiplicity of your 110 is your 12. So intensity also, that is also depending upon your the multiplicity. So the ratio of the first two peak will be the first one, if this is multiplicity, it's directly proportional to this multiplicity, 6 divided by the first peak, and it is the intensity and divided by 12, so this is the 1 by 2. So this is giving the ratio of the first two peak will be, the theoretical value will be the 1 by 2 1. Okay. Okay, this is about the this theoretical ratio of the intensity of the first two peak. Let's move to the next question. In next question, the XRD X-ray diffraction is used to determine which of the following characteristic of the character. What are the characteristics that we can examine with the XRDs? Because XRD is helpful to know about the crystal structure of this one. So which of the following? So is it helpful in the phase identification? Yes, this will give you the which phase is existing in your crystal. So this is also is used to determine the phase identification. Crystallite size, because we crystallite size we can calculate from the this peak width. If we know the FWHM of the peak, then I can calculate the crystallite size of the crystallite size of the this crystal one. So XRD is used for the crystal strain. Yes, strain is calculated with the help of your WH plot. WH plot, from WH basically there also we need the this your theta, the peak, and their FWHM value. From there we can calculate the strain also, how much strain there in the crystal one. And the third is the chemical composition. Now the chemical composition uh, is not determined by your XRD, but in the Ritwell refinement there is the one more further step in the XRD. If we do the Ritwell refinement, there we can calculate the chemical composition of your XRD. But for this XRD pattern, if we have given the XRD pattern, these are the only three peak, these are the phase identification, crystallite size, and the state we can calculate directly from the XRD pattern. Okay, this is about this question. Let's move to the question number 7. So, in a closed packed crystal, which of the following can be described by a stacking fault? So, uh, now in the A part it's AB, 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 AB. In the B part is ABC, 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 ABC. In C part is ACB, 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 then CBC, BCB, ACB, ACB, ACB. So there is change here also. In the D part also ABC, 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 AB, AB, then again AB, AB, then ABC, ABC, ABC. So what is the stacking fault? So stacking fault is basically a defect in the crystal structure of the material, particularly prominent in the material with the closed pack. It is prominent in your closed pack structure like the FCC or HCP1, and it represents a planar defect where the normal stacking sequence of the atomic planes is the interrupted one. So we have the this, I mean, if there is a repetition, there is a planar one. If this is following that one, I mean, there is a regular repetition of your this one, so there will be no stacking for there. If there is the irregularity in there, so we can say these are the defect in the crystal structure. So if you send this is the AB, so this, if this is A, then upon B, then again A, and then B, so there is no, this is following same thing. And also this is repeating also ABC, 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 ABC. But if you see from here, this is ACB, then again ACB, ACB, but you can see from this is the CBC, then again the BCB, then here. So there is this is the there is default, I mean here this is the defect in this crystal structure here. So this is the one is the stacking fault. We call this is the stacking fault. If I see in this option also, this is ABC, ABC, ABC. Now it is the ABA, BAB. So this is not satisfying this your repetition ABC, ABC one. Here also ABA again, then the BCA. This is not again, then the BCA. So this is not repeating one. So this is also the stacking fourth one. So C and D is the correct answer. Okay. So this is about the stacking fold one. Now let's move to the next question. Question number A. So the angular relation between the Berger vector and the dislocation line vector for a is displacement. So you know that this Berger and the dislocation line vector are the perpendicular to the each other. You know about this. So in the is location they are the perpendicular to each other. So this we have the two kind of the dislocation as so what are the dislocation characters? So we have the two kind. One is the edge dislocation and another is the screw dislocation. In the edge dislocation, we have this B is perpendicular to T. T is this T is your dislocation line vector. Dislocation line vector, and B is your the Berger vector. So in the screw dislocation, this B is parallel to T. If it is perpendicular, then it is the your A's dislocation. If it is parallel to this B is parallel to T, this is the screw one. So if I say if these are the perpendicular, and what will be the slip direction for the edge one? This is parallel to B, and in the screw one it is also parallel to B, but the direction of this dislocation line movement relative to B will be the in the edge one it will be the parallel one, because both are the perpendicular to the, so it will give you the parallel one, and in the screw one it will be the perpendicular one. So direction of the dislocation moment relative to B in the edge one it will be have the parallel one, and then in screw one it will be the perpendicular. For the edge dislocation, B is perpendicular T. In the screw one it is B is parallel to the T. Okay. So this for this one A will be the right answer because it is asked about the A's dislocation here. So the A is the correct answer. Okay, let's move to the next question. So which of the following is and are the zero dimensional defects? So what are the zero dimensional defect? Vacancy, zero dimensional defect are basically, if I'm saying zero dimensional will be the zero dimensional will come the vacancy, short key, interstitial, short key or the interstitial. These come under the 0 one. And if I talk about the 1D dimension, 1D dimension defect are the your dislocation are the 1D or one dimension defects, and the 2D will be the your grain boundaries one. So here it is asked about the 0 dimension. So this green boundaries belongs to 2D. This belongs to 0D. Short key defect. Interstitial will be also the 0 dimension. Dislocation is the 1 dimension. So B and C are the correct answer, and that are corresponding to the 0 dimension defect one. Okay, this is all about the question number 9. Now let's move to the question number 10. So which of the following are the referred as the equilibrium thermodynamic defect? So you know already that the professor has also told the equilibrium thermodynamic defect are referred to the vacancy that are also dependent upon the temperature one, and these are the vacancy at the at a particular thermodynamic that is dependent. N is equals to N equivalent exponential of minus of formation energy divided by K into me T. So this is the thermodynamic defect are your the vacancies are the your thermodynamic equilibrium thermodynamic defects one. So vacancy is called the equilibrium thermodynamic defects one. In next this question number 11, for a dislocation, for the screw dislocation, which is are the true. So we have already discussed about the this screw and the edge one. So the in the edge one we altogether this B is perpendicular T. This is for the edge one, and the if I'm talking about the screw dislocation, this B is parallel to T. And if I talk about the this movement, how the this movement will be the dislocation vector movement will be the perpendicular to the applied stress in your screw one and if it is parallel, vector B parallel to the apply this direction of applied stress, then it will be the S1. Okay, for the screw dislocation one, so this Burger vector is parallel to the dislocation line vector. So B is the correct answer. And in the C and the D part, so this location moves parallel to the direction of the applied field. No, this is in the edge one as dislocation, and here the dislocation moves perpendicular to the direction of the applied one. So this is the D part, and you can see also here because we have used these two property ones. So relation between the dislocation T and the B, in as it is perpendicular, in the screw it is parallel, and the direction of dislocation line vector will be the parallel in case of the parallel to the applied to the this applied stress and perpendicular to the applied stress in the screw dislocation. So B and D is the correct answer. Okay, so this is all about the question number 11 one. Let's move to the question number 12. So if someone has any doubt till this point, please ask your doubt, and or you can write in your chat box. So if till this point, if someone has any doubt, please let me know. No, okay. If anyone other has any doubt, There is no response, so I'm hoping it is clear till this point. If you have any doubt, just let me know. Okay. So let's move to the next question then. In the next question, the broadening of a peak in the X-ray diffraction pattern is ascribed to. One is the broadening of the peak. We have the two. If this is the XRD pattern, this is happening this broadening. If I'm considering this is the broadening, my peak get broadened. This FWHM got increased. That's why we are calling it the broaden. This peak is broadened. So this is because of the crystallite size, non-uniform uniform strain, and the position of the atom also. So which of the followings are the correct one for this one? So this broadening, you know this the crystallite size. How this crystallite size with the related with the or this FWHM. So you know we know that this T is basically T is my the crystallite size. This is equals to 0.9 lambda beta cos theta. Beta is your FWHM value. Okay, and this because if broadening means your FWHM get increased. Okay, if this increased, so your crystallite size will be the smaller. For the this, if I'm say for the the um, for smaller grain, we got the broad peak. We know this, and for the larger grain, if we have the larger grain, then we have the narrower peak one. So yes, this FWHM, this is broadening is dependent upon your crystallite size. If it is the smaller, then there it will be the broad peak. If it is the larger one, then it will be the narrower one with the or the more crystalline peak. So this crystallite size also define your broadening of the peak one. In the next one is the non-uniform strain. So if you have let's say if this is the XRD for the no strain one, if there is no strain, then this is your XRD peak, the peak corresponding to the, I'm considering the only one peak, so this is the XRD peak when there is no strain. Okay, when it will be the uniform strain. Uniform strain, I mean the whatever the crystal structure we have, if we having this one D values, if either D will increase or decrease. So in uniform, the all the diffraction pattern will be go aligned. I mean, it's not like it will decrease here or it will increase here. It will be the uniform everywhere. So either it all will decrease or either it all will increase. So once if it is decreased, because they follow the Bragg's law. Bragg's law is basically your 2d sine theta is equals to n lambda. N lambda is constant, your 2 is constant. So d sine theta. If d your increase, then theta sine theta is you know that is more or less is equivalent to theta. So your if d increases, then your theta will decrease, and if your d decrease, then your theta will increase because they have to follow this Bragg's law only. So this if this is the peak corresponding to the no strain, then if it is the uniform strain, so in uniform strain, so your either your D will increase or the decrease one. So if it is increased, then it will shift to the lower angle. If it is decreased, then it shift to the higher angle. So your peak will be like this way. It will say it's the same peak, but now it will either will at the lower angle or it at the higher one. The same peak, the same broadening, everything is same. But if it is not uniform, non-uniform. In case of non-uniform, so there will be some broadening, so it will decrease here, it will increase here, so there will be the mismatch. There is no uniformity in the strain also. So there will be, you can see there will be the broadening of the peak. There, you can see the broadening of, if this is corresponding to your uniform strain, this peak only shifted at the lower or the higher angle, then that represent your uniform strain. And if the peak got broadened, then it is representing your non-uniform strain one. Okay, so this non-uniform strain also uniforms also lead to the broadening of the peak. And the third one is the uniform strain. No, uniform strain does not lead to the broadening of the peak. It only shifts the peak at the lower at the higher one. So this is not the correct one. In the next part, the position of the atom. No, the position of the atom that will give you the intensity, because in the structure factor that will affect your structure factor. As I already told you, this F intensity, or yeah, this structure factor is a small f exponential of 2 pi I H nu. This, if I am for the n atom, so this will be the KVN plus LWN. Okay, so this position of the atom lead to your intensity, how your intensity changing. It is increasing, higher, no intensity or something. For the this position of the, so position of the atom does not lead to the broadening of the peak one. So this is also the not the correct answer. So C and D is not responsible. Basically, uniform strain and the position of the atom are not responsible for the broadening of the peak. Only the crystallite size and the non-uniform strain give you the broadening of the peak. So A and B is the correct answer. Okay, so this is for A and B is the correct answer. Let's move to the next question. Question number 13. So in question number 13, in the following figure, this is the following figure, identify the nature of the dislocation. So we know that dislocation, we have the two kind of the dislocation. One is the edge one and another is the screw one. There are the two. So now it is asked, so whether if B is perpendicular to T, then it will be the edge one. If it is making the this if it is at the uh, in the positive direction, then it will give the positive dislocation. If it is in the negative, then it will give the negative direction. So here it is seen here. So if this B is perpendicular, because applied stress is in this direction, and this is dislocation at the perpendicular direction. So this is at the perpendicular, B is perpendicular to, so this is the edge one, and this is at the upper one, because here it is happening. So this is forming the T here, this you can see here the T here. So this is giving the positive S dislocation, or I can summarize this as a S location can be visualize a scenario where there is no extra half plane. When there is an extra, because you can see this is the extra half plane existing here, you can see there is no one, but there is this extra one, and that this extra half plane lead to the your dislocation one. This is S, and once it is moved with the stress one, this is moved to the edge, and we can also find it here also. So the edge location is a scenario where there is an extra half plane of the atom inserted in the crystal structure or terminating within the crystal. In the schematic, this is the T-shaped arrangement. Okay, so this is the T-shaped arrangement. It is, you can see this is the T1. The extra half plane terminates within the crystal. This is because this extra half terminate within the crystal and creating a line defect that extend perpendicular to the direction of the external extra atom. So this is the extra plane. The plane along with the extra half line end is the, this is the what is the dislocation line vector? This is the line along which this end. So this is your direction of dislocation, and this is your Burger vector. So the Burger vectors that describe the magnitude and direction of lattice distortion, where the lattice distortion is coming. So lattice distortion due to the dislocation. In S dislocation, the Burger vector is perpendicular to the dislocation line, and the direction of the Burger vector define whether the dislocation is positive and negative, and how the positive and negative are defined. In the positive S dislocation, this Burger vector points in the same direction as the extra half plane of the atoms, and in the negative one it will show in the opposite to the direction of the extra half plane. So this figure represent the positive as dislocation one. So B is the correct answer. Moving to the next question. Now in the next question, identify the nature of the defect present at the A and the B and the C in the systematic diagram of the anion. This is the bigger one are the anion one, and the smaller one are the cation one. So you have to tell what kind of the defect are present in this lattice. So A part, the A, if it is A Frankel one, Schottky one, and this is your cation vacancy one. In the B part, the Schottky anti-Frankel cation vacancy. In the C part, this is the anion vacancy, this is your interstitial, and then the cation one. In D part, this is the Schottky and the Frankel and the cation vacancy. So this is the vacancy is basically absence of that one. If it's the cation one, then this is the absence of your cation one. Anion vacancy is basically the absence of your anion atom in that lattice. So what are the Frankel and the Schottky one? So the Schottky defect are basically when the equal number of the cations or anions are missing from their normal crystal structure. They are the both the cations and anions will miss from their crystal structure. Then it will giving the I mean the neutral behavior. So this is the for the Schottky defect. If I'm talking about the Frankel defect one, when your smaller anion or the cation are displaced from the normal one and occupy the interstitial. I mean, if this is something, this is the lattice, this is the cation one. Okay, this is your cation, these are the cation, and if I say this cation, now it is not here, it will remove from here and it move to here. So it is moving to the interstitial site. Interstitial is basically the at the not at the substitution at the atom location, that the at the interstice, I mean at the vacant space or the between the atoms, or the that is interstitial one. Substitutional, it replacing your atom, that the substitutional. Interstitial, it is going here and moving to the at the space between the atom anion and the cation one, there it is moving there. So that will give you the Frankel one. The in the Schottky defect, because both the cation and this are missing from the known ones, so the your density will decrease, because it is because one cation and one anion will remove from there, so there will be the density decrease. But in the Frankel one, there is no decrease in the density, because it is only just moving from one place to the another one, so density will not change. Or this is generally because both the cation will defect when we have the cations and anion of the similar size. So we compare, if we have the similar size, then we will say this is the Schottky defect. In the Frankel defect, when they have the difference in their size, cation and the defect, because so that it can occupy the interstitial site. So this is observed when your cations and anion are differ in their size. It is found in the it is found in the ionic solids having the high coordination number. Okay, and it is found in the ionic solid with it is for the low coordination number. So moving to this question, it is here in the Schottky. So Schottky, Frankel and cation or anion vacancy you have to find. So for the which are representing A and B and C. In the A part, if you see here, so this is the I mean this circle representing your A region. In the A region, if you say this I mean the positive, that we just define this, the bigger is the your anion and smaller is the cation ion. Okay, so bigger from here is the bigger one is the missing one. Bigger and bigger circle or the bigger anion is missing one. This one is missing, and from here if you see from the repeating one, this is also missing. It means one cation and the one anion is missing from this one. If cation and anion both are missing one, and we define this is the Schottky one. So A represent your Schottky defect. Schottky defect. Okay. Moving to the next part, in the B part, if you see here, Now if I'm going to this way, I mean this, so there should be here cation also, blue color one. It should be the blue color, so it is missing here. This is missing here, and this missing, and we can see from this here. Now here are the two one. So two one, I mean this missed cation move to here to interstitial side. So this is the interstitial side, na? Because otherwise the lattice having the, these are the position for the lattice one. These other these are the interstitial. This kind of the thing are the interstitial. So this cation is moving from this side to this to the interstitial. When this is the cation move or the smaller anion, because here the my cation is the smaller anion, air displaced from your normal side and occupy the interstitial, then it will represent your Frankel defects. Okay, so A is your basically Schottky defect and B is your Frankel defect. Okay, now move to this region. This is the C is the this region. So from here you can see this is cation, anion, cation, anion, cation, anion. This is right way. This is cation, anion, but here is no cation. This is missing, but anion, then anion. So in this region, all are thing, but this cation is missing. So there is no cation. So this cation is missing, means that there is the cation vacancy existing in, because now no other anion is missed here, and this is this no, missing cation is not moving to the other another interstitial site. So this is the vacancy one, the cation essence. So C is your cation vacancy defect one. So if I see the option, so A represent the your Schottky effect, B represent the Frankel, and C represent the cation vacancy one. So this will match with the D part. So D is the correct answer. Schottky, Frankel, A is the Schottky, B is the Frankel defect, and C is the cation vacancy defect. So for the so remember this, the Schottky defects when the equal number of the cation and the anions are missing from their normal site, and then in the Frankel when the smaller anion move from their normal site and move to the interstitial site, that will be the your Frankel defect. Okay, and vacancy is basically absence of that cation or anion from their normal site, and it is vacant. It is not moving to the another site. So that is the vacancy one. Okay, so this is all about this defect one. How to identify the what kind of the defect are present in the your lattice. Now in this question, this is the numerical question. It is asked the ratio of the equilibrium vacancy concentration in copper at 2000 degrees Celsius to the that of the 500 degrees Celsius each. We have to find the vacancy of the copper at basically over 2000 degrees Celsius divided by the vacancy of the copper at the 500 degrees Celsius, and Es is the energy required to move an electron from the interior to the surface. One is the 1 electron volt. So you know that this vacancy is the C constant and the equilibrium 1 constant, the exponential of minus is the surface energy by K and T divided by K and T divided by KT. Sorry, K and T, not the, it's KT. So how this, if I am considering, because this equilibrium vacancy consider that is dependent upon the temperature also, and we define the vacancy called the equilibrium temperature defect one. Vacancy we define in the earlier question we discussed this thing. Vacancy is basically your equilibrium thermal equilibrium defect one. So the concentration of this one will be defined by this. So this will ratio, if we, so here T is in your Kelvin. So T corresponding T1 is the 200 degrees 2000 degrees Celsius. So this will give you the in the Kelvin it will be the 2000 plus 273. So this is going to 2273 Kelvin. and T2 is the 500 degrees Celsius, so this represent the 500 plus 273, so this is giving you 773 Kelvin. Okay, and ES is given, that is the 1 electron volts. So we know this is the constant value. ES we already know. K is the constant value. K is of, if I talk about, because it here this is given in the electron volts, so K is the 8.85 into 10 raised to power minus 8.661 is basically, and it 10 raised to power minus 5 electron volt per K. Just you have to put these value in this formula and find out the concentration, vacancy concentration ratio. So if at the this I'm representing at the 2000, this is V1 or this is V2. So V1 by V2 will be the exponential of minus 1 divided by 8.61 into 10 raised to power minus 5, and temperature is 2273, and this is divided by, this is divided by exponential of minus 1 divided by 8.61 into 10 raised to power minus 5 into 7773. Okay, so this is the, now you have to solve this. See, you have, we have already put this equation and you have to solve this one. So once you solve this one, and you will find this V1 by V2 is the order of 10 raised to power 7, or it is going around 3. It will, if once you calculate these values, so this will give you around the 3 into 10 raised to power 7. So at the higher temperature it is having the higher vacancy. Okay, from this question, from this numerical, you can find out this at the higher temperature there will be the higher concentration of the vacancy one. Okay, so corresponding to that you will get the order of 7. So this will belong to around the A part. So A will be the right. Just calculate this value. We have already done the substitution. Just calculate, put the value back into calculate and do the calculation. Okay, so this is about the question number 15. Let's move to the next question. Question number 16. So in this question, the shear modulus of a copper is the 35 gigapascal. Lattice parameter of the copper is your 3.65 angstrom, and the magnitude of the Burger vector in the copper one is, in the Burger copper one, for the, if for the, because your copper is existing in your FCC lattice, for the FCC lattice it will be the A by 2, but the vector will be the 1 by 2 1 by 2. So B is basically A by 2 110 110, and what will be the magnitude of this one? If I say if I represent this is the one, so this will give you root 2, magnitude of this to A by 2 into root 2. So this is will give you A by root 2. So Burger vector in the copper will be B is equals to A by root 2. Now you know the A is basically lattice parameter for the copper is the 3.65 angstrom. Just substitute it here, 3.65 divided by root 2. So this will give you around, so this will give you around, this is 3.65 divided by, this is, this is something. So this will give you around 1 point, and no, this is giving around 2.5809 something, 9 angstrom. So B will be the this magnitude of the burger vector in the copper is this a by 2, because we know this is the a by 2 of the 110. So if I take the magnitude of this, magnitude will be the root 2, and once I put the value, this will give b is equals to a by root 2. So once we substitute the value of the lattice parameter here, we are getting around the 2.58 angstrom. So magnitude of, if, because this copper is in the FCC lattice, if it is in the BCC one, so the in the BCC lattice, the length of the this burger length of the burger, not the burger line vector. So this is the length of the BCC lattice. If it is the BCC lattice, then it will be the a by 2 of 111, and 1 will be give you the, this will give you the 3 root 2 a by 2 something, because this will give the root 3, so root 3 a by 2 for the BCC one. For the FCC one, it will be the a by 2. So shear modulus is basically the G, and we represent the shear modulus is represented by the B, is represented to the your magnitude of this length. And how this is, this is magnitude of the burger through the dislocation theory. Because of the dislocation, we have the dislocation, and there is there kind of the some kind of the shear modulus that is existing, and it is this the energy that is stored in the this your dislocation per unit length is basically proportional to your C lattice. So whatever the energy that is stored in the dislocation per unit, that is define your G and the or the B square one. Okay, so this is the shear modulus. So if you have to calculate for the FCC, then it will be the a by 2 of 110, and if it is for the BCC, it will be the a by 2 of the 111 vector. Okay, so this is about question number 16. Moving to the next question, question number 17. So in the question number 17, it is the shear modulus of the copper is the, this G value is around the 35 gigapascal. So this is the 35 into 10 is to power 9 pascal, and the lattice parameter A is equals to, for the copper is the 3.65 angstrom, and the what is the elastic strain energy per unit length of the dislocation line vector in the copper one. You know this, the elastic strain energy, U will define the U per unit length is half Z B square, and we know this G is equals to 35 into 10 raised to power 9 pascal, and B well we calculated from the last part, because for the this it is existing in your FCC one, so this is your B will be the 3.65 divided by root 2b. So once you put, so this elastic strain energy per unit value will be the 1 by 2 G is equals to 35 into 10 is to power 9 into B square will be the 3.65 divided by the root 2 ka whole square. Then it will give you 1 by 2 into 35 into 10 is to power 9 into 3.65 square, and divided by 2. So this will be the 35 10 raised to power 9 divided by 4 into 3.65 whole square. When you calculate it, you will find out, calculate this value. So you will get basically, you will get the 35 multiplied by 3.65 square multiply by, no, this is not the, multiply by 1. So this is giving you the around 466.2875 divided by 4. So this will get a 1 1 6 10 raised to power. Have I done the something? Oh, okay. This is in term of angstrom. So this is term of angstrom also. We have to consider this is angstrom square. So this is one. This is if I divide by 4. So this is giving you 116.571875 into 10 is to power 9 into 10 is to power angstrom minus 10 square. Okay, so this is giving you 10 to the power 9 into 10 to the power minus 20 angstrom is 1 angstrom is equals to 10 to the power minus 10 meter 1. So because all are in the SI unit, so we have to this take also this B value, this location line vector also in the SI unit. So this will give you around 116.572 into 10 is to the power minus 11, and if I minus 11, then if I calculate, so this is 1.16 into 10 raised to power minus 9 Newton per meter, because we are taking about the this is per unit length. So this is giving you 1.16 into 10 raised to power minus 9. So C is the correct answer. Okay. So 1.16, just you have to put the values in the formula. What is the, this is the latest strain energy per unit length will be the half GB square. So your G is basically, G is given, that is the 35 Pascal. So and the lattice parameter is also given, but in the last part we also calculate the dislocation vector. This is for the FCC1B will be the this A by root 2, and we know, and once we have the this elastic strain is equals to half GB square. G is 35 into 10 is to power 9. B will be the 3.65 divided by the root 2, and we have to take the square root of this one. And also we forget here take the unit of this angstrom, because we have already done this in the SI unit, but this angstrom also, so we have take also this value 10 is to power minus 20. Considering this one, this is 10 is to power minus 20, then you can remove it from here. So this will give you square to 10 raised to power minus 20 equals to, and substituting this one, you will get the 1.16 into 10 raised to power minus 9 Newton per meter. Okay, so this is about this question. Moving to the next question. Okay, so this is all about the question assignment number 8. If somebody has any doubt till this point or in the course one, so you can just let me know. We can solve that doubt and we can solve that one. Otherwise I will discuss this assignment one by one. So there is some discrepancy in the question number. I don't know, it is not saved, so but I will do it, and then before the uploading one. So in the first part, let's move to the one by one question. I will give you the brief, just the brief description of these question in the assignment number 8. So in the first A part, it is asked, so what I mean the what how the intensity and the structure factor that are related to your XRD diffraction. So what are the correct statement for the XRD diffraction? Structure factor, we know that that is the independent of your shape and the size. Intensity, we know that depend upon the structure factor, and the structure factor also depending upon the HKL value and the position of the atom in the unit cell, and it is also depend upon the atomic number also of the atomic number of the element in the crystal one. Okay, in the next question, because if it is given the FCC one, so what will be the first three peak, and it can be asked in the for the BCC one, what will be the 3B. For the simple cubic, we know that all the HKL value are the allowed. For the BCC one, that's H plus K plus L value should be the A1, and this and the if it is odds, and there will be the no. For the allowed one, this has to be even. For the FCC one, either all have the all odd or the all even. So this allowed will be the all HKL value are either order or the even one. If this is having the mixed behavior, so this will not give you any diffraction peak. So for the if it is asked in the FCC one, so just consider the HKL value should be such that all the HKL value either odd and the even. So if you see from the this in the one, so they are having the first A and B are having the mixed behavior in the C and D, because these are the both are satisfying the this condition. But there is this thing is we have to calculate the first three epic, and the first three correlate to the 111, 200, and 22. Then after this well 311 come out. So first three will be the 11, 200 and 2201. In the next question, because we know we if the theta is given, 2 theta is given, where we are getting the XRD pattern, and the first five for the corresponding to first five peak is given, and we have to find out these peak are corresponding to which crystal structure. Is it the simple cubic, the body center, or the face centered one? You have to calculate it, because once we know the 2 theta, then we can calculate the, because for the simple cubic we know this is to the all the peaks will satisfy the Bragg's law, that is the 2d sine theta is equals to n lambda. So corresponding to that, that's your d sine square theta divided by the h square plus k square plus l square equals to should be the constant, and this constant will be the lambda square by 4a, I guess. This should be the constant value. So sine square theta, because theta is given, 2 theta is given, from there we I can calculate the k this sine square theta, and the because simple cubic, and we know that the because the first five peak, if it is not mentioned the first five, then it is difficult to find out then which it is belonging, but it is first one, because we know the what will be the first one. So the first one we know the what will be the h square k square plus l square, or you know the HKL value. From there you can also calculate the h square plus k square plus l square value, and once you divide for the simple, if it is coming out the constant, then it is satisfying that, and then it that corresponding to that crystal structure will belonging to this 2 theta values. So if it is not satisfied, so that crystal structure will not represent these peaks one. So if you are getting the constant value, then that will be the correct one, and if it is you are not getting the constant values, then it is not the correct crystal structure corresponding to the these peaks one. Okay, the now again the diffraction condition for the BCC one or the FCC one we already discussed. In the another one, if we have given the alloy, then the extension condition will be such that you have to consider the both the one. So it will be the sum of them or divided by the 2 for the alloy one. You have to consider the both one 50-50%, and single crystal structure are examined by the following method: the Lee method and the rotation crystal method that we also discussed in the last class also. In the fifth one, we have the theoretical. What with the theoretical ratio of the intensity, because that also depend upon the multiplicity also. So multiplicity of the first two peak for the simple cubic will be the 100 and in the 110. So the multiplicity of the 100 is the 6, because we know that so the 100 will be the 0 1 0 0 0 1. We already discussed this thing, 0 0 0 1 minus 0 0 0 minus 1. So the multiplicity of this peak is the 6, and multiplicity of the 110 is the 12. So that also depend upon the ratio of the intensity. So that's why the theoretical intensity ratio of the first two will be the 1 by 2. The next question: the XRD diffraction method is used to determine the phase identification, crystal size, and the stain node, the chemical composition. One in the next one, it is the stacking fault. So what are the if it is repeating, it is following the same repeating unit across the crystal structure, then it is not having any fault. But it is if there is the misbehavior or the this is discontinuity or there is other repetition of unit, then it will be the stacking fault in there one. Stacking, I mean the fault in the stacking. If stacking fault means that there is the fault in the stacking. If it is I mean obeying the same rules, and then there is no fault. If it is not, then there will be the some sort. And next one is the delocation, that is your one dimensional defect. So these are the two types, as one and the screw one also. So in which the angular relation between the Yobaga vector and the dislocation, these are the perpendicular. For the screw one, they are the parallel one. Okay. This is about the dislocation, and zero dimensional is the vacancy or your short key, and the interstitial one, the zero dimension. First dimension defect will be the your this dislocation one, and the two dimensional will be the green boundaries one. In the next question, it is about the equilibrium, and the we call the vacancy are the equilibrium thermodynamic defect also. And the fourth same is next 11th question is same as the dislocation one. The next one, it is the about the how the broadening affects. So broadening is because of due to your crystallized size and then non-uniform strain also. The next question, and what kind of the is dislocation in the following figure? So it is having the positive is dislocation one. And you in the next question, and we have to identify which kind of the defect existing in the lattice structure. Frankel, when Frankel is basically when a cation or the smaller ion missing from the normal site and move to the interstitial one. There is the Frankel, and the Schottky when the cation and anion both anion are missing from their normal site, that will be the Schottky one. And vacancy is basically deficiency of the cation or anion corresponding to the cation vacancy on the anion vacancy. So at the equilibrium at this temperature, what will be the equilibrium vacancy? So that is also depending upon the temperature, and it is inversely it is directly proportional exponential of minus 1 by T. Other factor are the same, ES is the same both, so it's depending upon the minus 1 by T. So substitute these value and calculate the what will be the ratio for this one. And if shear modulus is given, so you can calculate the magnitude of the Baga vector for the FCC, BCC. For the FCC, it will be the A by 2 of the 110. For the BCC, it will be A by 2 of the magnitude of vector 111 vector. So this is all about. And what will be the lattice strain energy? That is the half G B square. So this is all about the assignment 8, and this is our last assignment of this course. And if you guys have any doubt, and I mean if you have any doubt, you can mail me, and I can write my mail here, and you can mail me, or either you can ask in the this in the discussion form also. There we will help you to clear out your doubt, or either you can mail me. I will reply to you. If you have any kind of doubts, just please let me know. Otherwise, we will wrap up this course with this assignment. This is the last assignment, and we'll hoping for your good exams. And okay, and so if you have any doubt, so please let me know if you have any. Please let me know if you have any doubt. If you have any doubt, just let me know. Then we will discuss that one. Otherwise, I will wrap this assignment with this course also as well, and we will finish. We will discontinue our meeting then. Okay, okay, Jacqueline, no ma'am. Okay, fine. Then, if you don't have any doubt, then I am just ending this meeting and hoping for your best exam and all the best for your coming exam. And if you have any doubt, just mail me, or you can ask in the discussion form. Okay. Thank you for being in the course and attending the TA session for this one. Thank you. So I am ending this meeting. Okay. Thank you.